Hello, yeah, this is Anurag. I'm starting a new series on analog integrated circuit design using ADS. Here, the entire series is going to be devoted to how to design op-amps, OTAs, and the circuits using these op-amps and OTAs. How to design basic gain stages, right? And how to design, more advanced circuits like switch capacitor circuits and all that. So I'm going to start this series with the 2 or 3 sessions on devices, electronic devices and circuits, and then I'm going to proceed to more advanced designs in analog circuits, right? So let's get started. So what I'm going to discuss in this session is devices, right? Electronic devices. So first and foremost which comes to my mind is you should know a p-n junction diode. Now, before even I go into um, a p-n junction diode, I would like to discuss something on semiconductor physics. It will be easier for you to follow p-n junction diode and other devices once you know semiconductor physics, right? So the next device I'm going to talk about is going to be a MOSFET, and the third device I'm going to talk about is going to be a BJT. Okay, so these devices I'm going to talk, but first and foremost I'm going to start with semiconductor. Sorry, yeah, I'm going to start with semiconductor physics. Semiconductor physics. Okay, so uh, first of all we should know what is the basic element, basic uh, ingredient of an element. An element is made up of number of atoms. So the basic particle which you should know is an atom. Okay, and atom, according to Rutherford's model, atom basically has got a central nucleus, and this nucleus has got a positively charged particles called protons, and these protons are heavy in size. They are heavy. Okay, so I've put here 6 protons, and there are neutral particles called neutrons which are almost equal in number. Okay, so this is what is nucleus. Now, as you know that, okay, so we have got protons which are positively charged. Okay, protons are positively charged. So now what is the charge on a proton? Okay, so we measure the charge in coulomb, right? 1.602 into 10 raised to minus 19 coulomb. Okay, so that's the charge on the proton. Okay, neutrons are electrically neutral. Now, why do we need neutrons, right? Because you know that like charges are going to repel each other, and that force of repulsion is going to be k into the q1 charge q2 over r square, where q1 is a charge on a proton, right? So if you take 2 protons, then it's going to be 1.602 into 10 raised to minus 19 square into proportionality constant k divided by distance between them. So basically the force reduces the square of distance between them. Now this force has to be overcome by some form of a gravitational force. Okay, so this will be equal to uh, let's say put here g into m1 into m2 over r square. Now these two forces are going to balance each other, and the nucleus is going to be stable, right? So this happens that now what happens is, if I just assume positive charges, then the atom is going to be positively charged, but it's not so, right? The atom is not positively charged. The atom is going to be neutral. So then there are, according to Rutherford models, there are electrons which are going around them, okay, in pairs in these orbitals like this. So I'm going to have 3 orbitals here like this, to account for 6 electrons here. Okay, so number of electrons are 6, number of protons are 6. Both have the charge, so electrons are much lighter than protons and electrons are negatively charged. Okay, so if there are equal number of protons and electrons, then the atom is going to be electrically neutral. So atom is electrically neutral. Okay, now these electrons are much lighter than these protons. Now if these electrons were stationary, they would just bump into the nucleus, right? But they are not. They are going around with a certain velocity, so they have a kinetic energy which is like half of mv square. So that is going to be the kinetic energy they have, where v is the velocity of electron. Now there is these orbitals, they are basically discrete or distinct, and what is distinct about them is that uh, the if they are going around with a certain velocity, they are experiencing certain centrifugal force, right? So for example, this is a positively charged nucleus, and there is a circular orbit in which these electrons are going, right? So now there is a distance, let's say r, where what will happen is that this centrifugal force is going to be equal to the centripetal force here, right? Centripetal force is because of attraction, and centrifugal force is because of them traveling around with their velocity. So when this balances, then the orbital is going to be stable, right? Now there are different orbitals here, right? So the way to do this is 1s, 2s, 3s, 4s, 5s, 6s, 7s, okay, 2p, 3p, 4p, 5p, 6p, 3d, 4d, 5d, and then you have got 4f. So these orbitals are not just circular in shape. Maybe the innermost, which is the s1, this is going to be more like a elliptic shape. But then p orbital, then d orbital, and f orbital, they are going to be different shapes. Now s orbital allows you to put in 2 electrons in s orbital, 2 electrons, sorry, and then p orbital allows you to put in 6 electrons. Then d orbital allows you to put in 10 electrons, and f orbital allows you to put in, I think it is 14 electrons. I may be wrong, I may be confused between 14 and 16, I think, or 18. Let's check it. Okay, whenever you in doubt, you should check it out. How many electrons in f orbital? That's the first one. Okay, 14 electrons, so I'm correct, right? 2, 6, 10, 14, correct. So I'm correct, so don't worry about this. Let's down this. Okay, so there are 14 electrons. We are clear on this one. Okay, so now the way you fill in these electrons, right? So for example, this is a carbon atom which I have just shown. Carbon atom got 6 protons and 6 electrons, right? And so these 6 electrons, they are going to fill in this. So the way they are going to fill in is based on the energy. They are going to start with the lowest energy, right? They're going to start with the lowest energy, then the higher energy, then higher energy. This goes cross like this, so it will be like 1s, okay, then you are going to have 2s and 2p, then you are going to have 3s, 3p, then you are going to have 4s, then you are going to have 3d. So that's how it's going to fill in, 4s, 3d, then you are going to have a 4p, and then 5s. So that's how it's going to fill in based on energies, right? Now the each orbital, okay, so basically a suborbital. P has got basically 3 suborbitals, right? D has got 5 suborbitals, and F has got 7 suborbitals. So each suborbital is going to fill with 2 electrons. Now, why there are 2 electrons? Because it's not just the electrical nature, it's basically the magnetic nature also. So these electrons are basically spinning, okay, with a certain axis. And so if there are 2 electrons which are spinning with the opposite axis, right, one is going clockwise, other is going anti-clockwise, then the magnetic field generated because of this spin is going to cancel out. So they are going to fill in pairs based on energy from lower orbitals to higher orbitals. This is known as Pauli's exclusion, exclusive principle, right? So that's how they are going to fill in. Now, for electronics designer, it is all about electrons, right? So when I say it is all about electrons, then that's what electronics is. It's all about electrons. Now, uh, the elements have atoms, and these atoms are unique, right? Unique in number, right? So that is known as number of, sorry, atoms have got protons which are unique in number, right? Like for example, hydrogen has got a single proton, right? So helium has got 2 protons, right? So that's how it is done, right? So the number of protons is unique in an atom. Number of protons is unique to an element, unique to atom of an element, So I can fill these atoms in columns and rows, and that's referred to as periodic table. So number of protons is also known as atomic number. Sorry. So atomic number. Number of protons and neutrons is called atomic mass. And so atomic number is what we are, which distinguishes an element from another element. So H, He, Li, Be, B, C, N, O, F. So what I'm writing is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, okay, and F is what? B, C, N, O, F. F is fluorine, right? Okay. So now this is based on something called valency. So let's discuss that. So there are 2 rules for an atom to be chemically stable. One is called the doublet rule. Sorry, I do a typing mistake. Doublet. That means that in the outermost orbital, which is the highest energy orbital, that is also known as a valence orbital. Okay, so the highest most orbital should have 2 electrons, or there is an octet rule. I think TAT. As octet rule means that the outermost orbital should have 8 electrons. Electrons is spelling mistake. Okay, so if it is a doublet rule or an octet rule, if that is satisfied, then the atom is stable or element is chemically stable. So element is chemically stable. Okay, when the atom is chemically stable, then the element is not going to react. So that way helium has got 2. So helium got 2 electrons, that means it satisfies the doublet rule, then stable. Lithium has got 2 in this and then 1 in this, so that makes a total number of the atomic number to be 3, right? So if you go for, so you can keep on filling like this. So for example, let's look at carbon. Carbon is 2s2, sorry, 1s2, 2s2, sorry, this filling is slightly off. Okay, so how do you do that? It's going to be 1s2, this is going to be 1s2, 2s1, and this is going to be 1s2, then 2s2, and then 2p2. Okay, so now the outermost orbital is the second orbital, which has got 2 plus 2, 4 electrons. Okay, now silicon, okay, is going to be atomic number of 32. So it's going to be 1s2, 2s2, 2p6. So that makes 10, 3s2, 3p6. So 1s2, 2s2. So how does it go? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, right? 3p6, 4s2, and then 3d10, 4s2, 4s2, and then 3d10. So this is 10. 10 plus 12 plus 6 is going to be 18 plus 2, 20, and 30. And 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so there is something wrong in here. Silicon has, sorry, it's not silicon. Let's look at, okay, let's look at these atomic numbers. Okay, these I don't remember on the top of my head, so let's basically go back to atomic number of, or periodic table. Okay, so let's go to the periodic table. Sorry, so I'm going to look at periodic table. Okay, so let's look one of the periodic tables. Why it's so blurry? Okay, so let's look here. Carbon has got atomic number of 6, silicon has 14, and germanium has 32. So we will go and find out the electron configuration for this. Okay, so let's go back. Okay, so this is carbon. Silicon has got 14. So I was messing up. Silicon has an atomic number of 14, right? So it is going to be 1s2, 2s2, 2p6. Okay, so that makes 10. Then you have 3s2 and 3p2. So again it has got 4 electrons in the outermost orbital. That is, these are known as valence electrons. Right, so there are 4 valence electrons. Now let's look at germanium. 1s2, 2s2, 2p6, 3s2, 3p6. Then you are going to have 4s2. Then you are going to have 3d10. Okay, then you are going to have, after this, 4p2, I think. Let's see again. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Okay, so it's going to be that. So let's sum them up. So this is 6 plus 4 is 10, 20, 28, 30, and 32. So it again has got 4 electrons in the outermost orbital. So you see, this is a group 4. This is a group 4. Correct? Now, this group is a special group, and all the electronics is dealing with this group. Now, besides that, there is a group on the left side, okay, which is going to be group 3, and there is a group on the right hand side which is called group 5. Okay, so we can have elemental semiconductors, which is usually carbon, silicon, germanium. These are elemental semiconductor. Okay, and then you have got group 3 elements, and these group 3 elements you can see. Okay, so these group 3 elements are boron, aluminum, gallium, indium, and whatever that is. Okay, and then group 5 elements are nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, so this is group 3 and this is group 4 and this is group 5. Now these are important. Okay, so now we can have elemental semiconductors using group 4, or you can have a compound semiconductor using the two of this. For example, I can have gallium arsenide. So gallium arsenide, I can have gallium nitride, right? Gallium nitride. Okay, so we will see this, why we have this and what is special about this, why they are important in semiconductors. So I'm talking this term semiconductor again and again, so I have to describe what that is. Okay, so now what happens is, okay, according to the rule, okay, the doublet or octet, there has to be either 2 or 8 electrons in the outermost orbital, right? Now here there are 4 of them. That's a halfway between 8 and 0. Okay, so now let's say we pick up sodium, right? So sodium in lookup table, in the periodic table, let's see, sodium Na is going to be 11. Okay, so that means that it has one valency of 1, right? So it has one valency of 1, so this has 1 as the valency. Now Cl, chlorine, okay, it has a valency again of 7, and then carbon somewhere in between has a valency of 4. Now what does it mean? It's like this. Na, to complete this octet, it's easy to lose one electron. So if Na loses one electrons, it has one positive charge. So atom becomes positive, it becomes an ion. Okay. Then chlorine, it is easy to gain one electron to satisfy octet. So now if this happens, okay, so it is like, it is like Na is a poor person. It has no problem losing one electron. Cl is a greedy person. It has always wants to have one electron. And then poor and greedy are together all the time. So if you see outside in the society, you will see wherever there are rich people, they are beggars, right? So they coexist. So this is what is the analogy here. So Na and Cl have these electrostatic charges, and then they stick together because of these charges, and that makes NaCl, right? So this is known as electrovalent bond. Valent bond. Sometimes my typing is, because you get used to word, and then when you come to writing you have problem with the spellings. Electrovalent. Okay, so you have electrovalent bonds. These are based on electrostatic forces. Okay, so one is positively charged ion, the is negatively charged ion. They are held together by electrostatic force. Now carbon is like a middle class. Okay, it's neither rich nor poor. And how middle class people stick together? Middle class people stick together by sharing. So in anything they want to share. So if they go for lunch or dinner or anything, they are going to share. So that's what a middle class stuff is. Okay, so carbon, silicon, germanium, they are going to share. So this form of sharing, okay, is known as covalent bond. So there is an electrovalent bond, there is a covalent bond. Now what does it mean, covalent bond, right? It doesn't mean that they are going to really share. They are going to be like, they do this common lottery system, right, where they will put in money every month and then they will withdraw a slip, and then all the collected money goes to one person, right? So this is this kind of arrangement. So if carbon basically forms a bond with 4 neighboring carbons, right, so that's how I represent it, then it doesn't mean that they are static in space. They are not static in space. It's just that for a certain period of time, all the 8 will belong to, let's say, one of them. So all the 8 will belong to this, and then in some other time, then all 8 will belong to this one. So it's basically shared in time, right? So it's not that this is going to be, they are still going around the nucleus, right? It's just that they belong to a certain atom at a certain period of time, right? So this is what a covalent bond is. Now, similarly, silicon will also form covalent bonds. Sorry. Okay, so this is the elemental form of sharing. Okay, so now we have got electrovalent bonds, covalent bonds. Now, if you take electrovalent bonds, like for example NaCl, right, there are no electrons for conduction. So basically NaCl is not a conductor unless you put it in water. When you put it in water, then Na plus and Cl minus, they kind of mix out with water, and now you can basically conduct electricity because now Na and Cl are movable, they are not fixed. So that's a electrolyte, right? So electrolyte is going to be conductive, but a powder form of NaCl, okay, is not going to be doing that, right? So that's what the electrical conductivity is. Now with covalent bonds, right, uh, they can become conductive, right? So now the question of conductivity comes. So what happens is, when carbon has got 4 outermost electrons, okay, so this is a carbon nucleus and there are 4 electrons which are going around in the outermost orbital. Okay, so this is the highest energy. So if I take energy, and by the way energy is measured in electron volts, then these valence electrons have a certain energy. This is known as valence energy level. Now if you apply certain energy to one of these electrons or more of these electrons, then these electrons are going to shift up in orbital. So basically what we discussed was, these orbitals are unique in the energy of the electrons. So once you supply energy, these electrons are going to go to a higher orbital, right? Now you apply sufficient amount of energy, which is known as band gap. So if you apply sufficient amount of energy, which is equal to a band gap, then these electrons are going to become free of the hold of this nucleus. So basically nucleus is holding an electron through a electrostatic force. Now when the distance becomes too high, then this electron is no longer under the influence of its nucleus, right? So then this minimum energy to extract the electron from its valence band is going to be uh, energy band gap, right? So that's called band gap. And the minimum energy that the electron can possess and still be free, that is known as conduction energy level. Okay, so we have got energy band gap separating valence energy and conduction energy. Now this is true in case of gaseous atom. Now if you bring these atoms closer and closer, so the gaseous state is going to go into a liquid state and then to a solid state. Now if I bring this another carbon atom close, then this valence electrons is seeing a potential energy because of this parent carbon, but also because of this carbon which is nearby, right? So now what's going to happen is, this this valence energy level is going to split up into sub levels. Now how many sub levels are going to be there? It depends on how many carbons are fitting close to each other, right? So what's going to happen is, so usually when they say energy band diagram, okay, they have this axis. This axis is interatomic distance. So if you take this and you reduce the interatomic distance this way, then this is going to split. Okay, so this is going to split. I'm going to leave it here. Split it into number of subbands. Okay, so let's say the number of subbands is NV. Okay, now same thing is with the conduction band. Okay, it is also going to split, but something interesting happens over here. Okay, so it's going to be more or less like this, or or I can draw it differently. People may get confused. Okay, so these are your subbands here. So this is going to call NC. Okay, so number of subbands in conduction band. So this is now no longer a level. It is called conduction band. And you know the origin of each sub energy level is because of a distinct nucleus of carbon. So more the carbons you bring together, the more the number of sub energy levels. So you have got NC and V as the number of conduction sub bands in conduction band, and NV is number of sub bands in valence band. So this is called conduction band and this is called valence band. Now, so up to here I have a gaseous state, and then you have a liquid state, and then you have a solid state. So usually when people draw a band diagram, they just don't mention what is on this axis. They just say that this is conduction band and this is valence band and this is energy band gap. So this is conduction band and this is going to be valence band. Now entire electronics is just the play of this valence band and conduction band. Now I'll explain you how. Okay, now if this band gap, energy band gap, okay, if this band gap is small, or rather it doesn't exist, so for example if I consider metals or conductors, then conduction and valence band, they overlap. Okay, so if this exists, then what happens is at any point of time, okay, at any temperature, you have got electrons in conduction band, and these electrons are not tied to any nucleus. They are free. They are free to move around. So whenever you apply a potential, they are going to move. So that's how this is called a conductor. Now in case of insulators, on the other hand, okay, same energy band diagram looks like this, that you are going to have a distinct valence band and conduction band, okay, and this is going to be separated by energy band gap. Okay, and then this energy band gap, so this this y-axis is energy in electron volts. Okay, so how do you convert energy into electron volts to volts, to joules, by multiplying it with 1.602 into 10 raised to minus 19. So that's how you're going to convert energy in electron volts into joules. Okay, so keep that in mind. So now this band gap in case of insulators is of the order of 6 to 12 electron volts. Okay, now if I was to apply energy to the electron which is bonded strongly to this nucleus, right, then I have to apply more energy, and if I keep increasing the energy, at some point of time this electron will break free from the nucleus, hold of the nucleus. That's what will happen, is that the electron will be available for conduction, and what will be left out, so for example, so what will be left out would be a in a covalent bond. For example, in a covalent bond, one of the contribution is missing, so that can be treated as a whole. Okay, so we will talk about this later on, but this gap is too large. If you apply energy in any form, okay, that's going to basically break down the material, rather than promoting an electrons from valence to conduction band for conduction. So these insulators do not conduct, so they are non-conductors. Now there's something in between where this and this, valence and conduction band and energy band gap. Okay, so what happens is, if this is of the order of, let's say, 0.3, electron volts to, let's say, 6 electron volts. So there is no distinct, very distinct 6 electron volt. It can be, 5 electron volts. So it's not very clear. This margin is blurred. Okay, so this would be called a semiconductor. Now, in a semiconductor, you can apply energy to promote an electron from a covalent bond. So there is electrons here. So it's all a question of electrons. Okay, so you can promote one electron to jump up, okay, and to go here. So when this electron jumps up to go there, you can apply this energy by many ways. You can apply this energy by using a photon. You can apply this energy by using a stress. You can apply this energy through temperature, by raising the temperature, right? So if you raise the temperature, electrons will jump from valence band to, so in terms of bonds, what is going to happen? Let's say this is silicon, and silicon has formed 4 covalent bonds, because then it will be octet rules satisfied. Now, if you have, so each line represents one electron. So if you apply energy to one of the electrons, so this electron is going to become free. So this electron is going to be bumped out, and what will remain behind is going to be lack of an electron. That I would call as a hole. So hole is going to be positively charged, and it is going to be same positive charge as this on an electron, but this is a fictitious, this is not a particle, it's a fictitious quantity. Okay, so when electron jumps, it leaves behind a hole. So electrons and holes are generated in pairs. So electrons and holes are generated in pair, right? So now what's going to happen? This missing electron, what can happen is, let's say there is another silicon here. So that missing electron can basically, electron from the neighboring silicon can jump into this missing electron, and that way if the field is applied, then electrons are going to move one way. So basically, if this is positive, this is negative field applied here, so electrons are going to travel that way, while the holes, which are going to be fictitious particles, they seem to be traveling this way. So now the question comes is, how would the holes move, right? The holes cannot move within the valence band, so they have to jump up and then jump down. So that's how they hop from one atom to another atom of silicon. So if electrons are subjected to a field, they are going to be attracted towards the positive terminal, while the holes are going to be attracted to the negative terminal. So if electrons travel in one direction, holes travel in the other direction, right? So this is referred to as drift current, which is based on a force due to an external electric field applied. So this is going to constitute a drift current. Okay, now there are going to be 2 drift currents here, electron current, hole current, right? So we have a concept of hole. Now hole has a charge of plus 1.602 into 10 raised to minus 19 coulomb. Okay, this is because the absence of electron is there. Now there is also going to be a mass associated with it. Now what do you mean by mass associated with this? So if electrons move in one direction, and equivalently the vacancy or the vacancy of electrons moves in the other direction, okay, then this is seeing certain restriction, and that is going to be the effective mass of hole. Effective mass. Now if the nucleus has a very strong force on these electrons, then the mobility of a hole is going to be less and the mass is going to be high. So let's go back to the periodic table. Okay, so let's look at gallium, and then silicon is over here, okay, and then arsenic. Okay, so what's happening over here is the effective mass of hole in silicon is less compared to effective mass of hole in gallium. So what it means is that the mobility, okay, so what is the mobility? Okay, let's define that. I'm not assuming you know anything. So okay, V is equal to mu n E, where V is the velocity, E is the electric field. So velocity per unit electric field is going to be called mobility. So this is mobility of an electron. Okay, similarly you have mobility for hole, and this depends on the effective mass of the particle, and this hole is nothing but a fictitious particle. Now it really depends on how strongly these valence electrons are tied to silicon. If they are very strongly tied, then the hole mobility is very low, or the effective mass of hole is very large. So gallium or gallium arsenide, so gallium exists as a binary compound, gallium arsenide, has got hole mobility which is 80 times of electron mobility. So roughly hole mobility is equal to 80 times of electron mobility. So that means that I cannot use a device which uses hole for conduction. Now in case of silicon, hole mobility is 3 times roughly of electron mobility. That is why we do not see PMOS devices in case of gallium arsenide or gallium nitride, while we see here there are NMOS devices or PMOS devices for silicon, but same is not true for gallium arsenide. So this is the reason why we don't have a CMOS kind of a process in gallium arsenide. We have NMOS only process, while in silicon you can have, or even germanium, you can have both CMOS and NMOS, right? So this is going to be a bi-CMOS process. Okay, in one case, okay, sorry, I have written it opposite. So this side basically is PMOS, this side is NMOS. So PMOS and NMOS. Okay, so we are going to have both devices in silicon, while in case of gallium arsenide and gallium nitride we are not going to have both devices. We are going to have only one device. This is all because of the mobility. Now this is something which is very simple stuff. Now we are going to deal with semiconductors only. Now semiconductors, okay, again are going to be elemental in nature, and these are silicon, carbon and germanium, while then they are going to be compound semiconductor which are going to be binary. Okay, these are going to be gallium, third and fifth group, arsenide, gallium nitride, indium phosphide, aluminum arsenide, okay, and stuff like that. Now there is going to be ternary compounds also. You can have a gallium aluminum arsenide, indium gallium arsenide, and so on, right? And then you can also have quaternary, which is going to be 4 elements. So these are all material systems. Now why do I have so many material systems in semiconductor design? Okay, so I'm going to show you a very important chart here. Okay, now in this chart I'm going to tell you that these all are crystalline in nature. What do you mean by crystalline in nature? They have got a small cell, a cuboidal cell here, right? Okay, this repeats along x, y and z direction to make a crystal, right? Okay, so the basic cell here has a certain dimension here. Okay. understand. Here you should understand that semiconductor physics, okay, has lot to do with just uh, band gap tailoring, and it all has to do with matching the lattice constant, and that's what makes the semiconductor industry very attractive, because you can do a lot of stuff with this kind of band gap engineering. So we will see when I discuss a heterojunction bipolar transistor, HBTs, then I can compare HBTs from different manufacturers, like for example Timic, Germany, or Atmel process, and or IHP process versus IBM silicon germanium process, right? So that is a discussion, whole another area of discussion. Which devices are better in terms of linearity, in terms of base transit time or FT of the device and stuff like that. So I'm not going to discuss that over here. I'm just going to leave at this note. So today I have covered a little bit of semiconductor physics, which we are going to carry on. Now, why is this important? Most of the books, they don't deal about this, and when you go into industry and you are suddenly faced with silicon germanium, for example, you are blank. You do not understand what's going on, right? Same thing is when you are introduced with gallium arsenide or nitride, and you don't know how it compares with silicon, right? Or silicon germanium, right? So so where to choose what, you don't know, right? So you are supposed to know all this kind of stuff being a designer, right? Which you do not learn in the books. There are some books, but they are very few in numbers, right? So I'm going to stop here for the first lecture on uh, analog integrated circuits using ADS, and I'm going to carry on in the next session with the devices, right? So thanks a lot. Thank you.